In the previous video, we talked about how we have this magical ability to find a topological ordering of the SECs of a digraph by looking at the highest post number in each SEC and then basically ordering them in descending order of that number. And what this meant is that if I find the post number, or if I find the post ordering, the vertex with the highest post number has to be in a source SEC. Unfortunately, for Kosaraju's algorithm to work, I need to find something in a sink SEC. So what can I do to find something in a sink? Well, what we're going to do is we are going to use the reverse graph to turn sources into sinks. Or actually, we're going to do the other thing around, to turn sinks into sources. The reverse graph is just what I get when I reverse all the arrows. So let's go ahead and find, just for the sake of example, find the reverse graph of this guy up here. So I'll do this in like maybe red just to show that we're looking at a different graph, or I'll just invert the colors. That'll be fun. So we'll have A, B, C, all the same vertices, maybe spaced out a little differently because I don't have that much room. F, G, H, I, J. But now I'm going to switch all the orders of the arrows. So all I'm doing is switching some orders around and forming a new graph. Oh, I almost drew that arrow the right way. Let's make sure it's going the wrong way. And then we also have some arrows doing some stuff over here. Okay. And there's a couple things we notice. First of all, the SECs are the same. In fact, the SECs are the same. And actually the metagraph, this is going to be, so let's, first of all, what are the SECs? Well, we have A, B, C, still an SEC, because in order for it to be an SEC, for two vertices to be in the same SEC, I need to have a path from one to the other, then back again. So if I already have both those paths, and then I switch all the arrows, I'm still going to have a path from one to the other and then back again. It's just those kind of switched roles. So the path that used to go from A to C is now a path that goes from C to A. But remember, I still had a path from C to A. That was CBA. That now becomes my path from C to, or it becomes my path from A to C, just going backwards. So yeah, I had a path from A to C. That turned into a path from C to A. And I had a path from C to A. That turned into a path from A to C. So the strongly connected components are going to be the same. And the metagraph of GR, we call this GR, is the reverse of the original metagraph. So let's keep finding our strongly connected components. Again, we've kind of justified that they should be the same. And now instead of ABC pointing to DE, DE points to ABC because that arrow got reversed. Similarly, F points to ABC, GHIJ points to F, all that reverses. And what this does is, remember, you can think of a sink as something where all of the edges all the edges it touches go into it. A source is one where all the edges it touches go out of it. So if I reverse the graph, my sinks and sources are going to swap around. In fact, even more generally, you can say that if you reverse a topological ordering, of G, you get a topological ordering of GR. And keep in mind, if we're talking about topological orderings, we're really talking about DAGs, and this would be referring to the metagraph. The metagraph, if you reverse the topological ordering of the metagraph, you get a topological ordering of, if you reverse the topological ordering of the metagraph, you get a topological ordering of the reverse graph. So what does this tell me? Well, the big thing it tells me is, let's see. So we knew that this was a source because it was the last thing in my topological ordering. Nope, because it was the first thing in my topological ordering. I also know that the last thing in my topological ordering is a sink. So if I look at the reverse graph, what I find is that the sink of the reverse graph, actually, no, that's not what I want to say. The source of the reverse graph is a sink of the original. Why? One way you can say that's true is because in the reverse graph, if it's a source, all the edges go out of it, which means that in the original graph, all the edges go into it. Or you could say reverse topological ordering. We said that the first thing in topological ordering is a source, the last thing is a sink. So if I'm reversing the topological ordering, something that used to be first in topological ordering is now going to be last, and something that used to be last is now going to be first. So our sources and sinks are all going to switch. So now, what does this tell me? I need bigger stars. Remember that the whole key to finding to identifying and exploring these SECs was to find a sink SEC. So what I need to do is to find a sink SEC in G. We need to find a vertex in a source SEC in the reverse, which is the vertex in last in post order. It's the vertex with the highest post number. Lots of exclamation points, because that's exactly what we needed to find. So if I take my graph and reverse it, and then find a post ordering, the vertex of the last post order will be in a sink of my original graph. And then if you remember, if I delete all those vertices, I'll kind of scroll back up. If I delete all the vertices in my previous SECs, the remaining vertex with the highest post number in the reverse graph is a source SEC of the reverse graph, which means that if I delete all the vertices the original graph, that vertex with the highest post number in the reverse graph is now a sink of what remains of my original graph. So we can use this process by taking this reverse post ordering of the reverse graph and then basically use that to keep finding sink SECs, which is what we need to do. So let's kind of outline this process at a kind of high level. So how do I use this? First, I'm going to get a reverse post ordering of the reverse graph. Then I'm going to take the vertex with the highest post number, and I'm going to explore from there. Explore from, I'll say from the first vertex in that ordering. In my original graph. And here, I'm just going to make a comment here. There's a lot of reverses that happen, but they're all like in the first step here. Oh, okay, there's going to be one other thing that happens later. Okay, so explore from the first vertex in that ordering in my original graph. To get the SCC, delete the SCC, or ignore it. And then last but not least, I'm going to explore from the first remaining vertex in my ordering to get the next SCC. And what this is going to do is this not only gets me my SCCs, this gets me my SCCs in reverse topological order. So there's one more reverse coming at you. Because I keep finding things that no edges go into. So the first thing, no edges go into it. Sorry. I keep finding things that no edges go out of. So the first thing, no edges go out of it. Then the next thing, no edges go out of it except for maybe the first thing. The third thing, no edges go out of it except maybe the second, which is kind of the reverse of what I'm looking for in a topological ordering. You can also see that based on this big claim that we proved way back here. So if I order the SCCs in descending order of the highest post number in the SCC, this is a topological ordering of the SCCs. What we're essentially doing is we're exploring them in this order, but of the reverse graph. So what we're doing is I'm ordering the SCCs in the reverse graph in descending order of the highest post order, and that's a reverse topological ordering of the SCCs in the graph I'm actually looking at. So it gets me everything I want in reverse post order, or in reverse topological order, which is, good to know. If I need them in topological order, I just reverse the order. Again, lots of reversing is going on here. And just to kind of pin things down, make sure that we feel good about this, let's go ahead and actually run Kosaraju's algorithm on the graphs we have here. So I'm going to copy and paste these. Give me a moment to do so, and then we'll get going. Okay, so I have my graphs. I've temporarily forgotten what the SCCs are so that I don't accidentally cheat. And let's go ahead and actually run this algorithm. So the first thing I want to do is find the reverse graph. And I already did that. Then I want to find, basically I want to find the post order of the reverse graph. So I'm going to basically run a depth first search on the reverse graph. How I like to do that, and I'm weird, basically what I do is I keep a little line of pre and post numbers. It looks like we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's going to end up being 20 numbers. Actually, the numbers themselves don't matter. What matters is the order, and I'm going to keep track of that. So I'm going to start by exploring A. When I look at A, and again, I'm looking at the reverse graph here. From A, I go to B. From B, I go to C. From C, I go back to A, but I've already seen A. And there's actually nothing else coming out from C, so we're done processing C. What about B? Well, nothing else is coming out from B. And then what about A? Nothing else is coming out from A. Okay, so let's go back in alphabetical order. Then I'm going to look at D. D has an edge to C, but I don't care about that because I've already finished processing C. But it does also have an edge to E, so we get that. And then, of course, E doesn't go to anything else. D doesn't go to anything else, so we're done there. Then I look at F. F obviously goes back to B, but that's okay because I already looked at B. So, and it doesn't go to anything else, so we're done with that. And then from G, we're going to look at, let's look at G. G goes to I goes to J. Actually, I goes to H before it goes to J. Because I'm doing alphabetical order here. So I goes to H. H doesn't go to anything new, so we're done looking at H. But I also goes to J, and then J doesn't go to anything else, so we're done looking at J. And then we're done looking at I, and then we're done looking at G. So we're actually done here. So my reverse post order of the reverse graph is going to be G, I, J, H, F, D, E, A, B, C. In this case, we see that they're very clearly organized into the SECs already. That's not always the case, so don't trust for that to happen. These can be mix and matched a little bit depending on what your graph looks like. This was just a very simple graph. Okay, so we found the post order of the reverse graph, and now we're going to explore in that order. So let's see. I'm going to start at G, and from G, I can get to, I'm going to draw this over here. From G, I can get to H, and from H, I can get to I, and from I can get back to G, but then I can also get to J, and then that's really all I can get to there. So that finishes exploring this. So we took care of that. And that gets rid of all of these guys. The next one I want to look at is F. If I explore from F, well, everything else that it gets to I've already looked at. If I was running DFS, I would have had these marked as already visited, so I wouldn't necessarily do anything with them. So you don't necessarily have to delete them per se, you just need to mark that they've already been visited so that you don't try to explore them again. So F, I don't really do anything with. It's just kind of there. And I explored from F and didn't get anywhere else. So we crossed that off my list. Now I'll start exploring from D, see what I get to. D gets me to E, E gets me back to D, but it doesn't get me anywhere else. And again, this is all in the original graph I'm looking at now, not the reverse graph. I used the reverse graph to get my ordering, but that was it. So I'll cross those out. And then last but not least, I'll explore from A and see where I get to. I get from A to C, I get from C to B, and then everything else has already been visited. So I don't worry about anything else there. And voila, without knowing what the SECs were in advance, I have just found what everything was. So what did I do? I explored from G. I got as far as I could. When I finished exploring, I knew that I was done with that strongly connected component, so I moved on to the next thing in my list. Started with F, did as much exploring as I could. When I knew that I was done, I moved on to the next SEC, and so on and so forth. So we would label this first one maybe 1, then the second one we might label 2, then this one 3, then this one 4. And we can add in the edges that the metagraph needs, right? I have an edge from F to G. I have an edge from actually ABC to F. I have an edge from that to there. That's what this looks like. And what we see is if I go backwards in the order of that I found these, it is a topological ordering. This one is, well, actually, no, what does that mean? Basically, it means that for each of the edges I have here, the number on the first one is bigger than the number than the second because it's a reverse ordering. So on this edge, 4 is bigger than 2. Great. On this one, 4 is bigger than 3. Great. This one, 2 is bigger than 1. Great. So if I reverse that order, I'm going to get a forward topological ordering of this, and life is good. So not only does Kosaraju's algorithm help us find strongly connected components, it also gives us a reverse topological order of them. So what does it boil down to? It boils down to finding the post order of the reverse graph, and then using reverse post order of the reverse graph to explore my original graph. And then after I finish, basically after I explore everything I do, I say that's one SEC, I move on to the next, so on and so forth. And when I do that, that's going to give me my SECs in reverse topological order. So there you go. There is the final step of what makes Kosaraju's algorithm work.